Okay, welcome back for our continuing discussion on solutions. We're in chapter 13. Hopefully you folks have mastered the art of writing molecular, ionic, and net ionic equations, and you've learned your solubility rules. Today we're going to shift gears a little bit and talk about something called colligative properties. Now the definition of a colligative property would be properties of a solution that depend upon the number of particles, not the type. For example, would the color of a solution be a colligative property? Think about this for a little bit. If it is a colligative property, then the color of the solution depends upon the number of particles, not the kind dissolved. I claim that the color of the solution depends upon the type of particle dissolved. For instance, copper sulfate solutions would be blue in color, wouldn't they? Cobalt chloride or cobalt nitrate solutions might be pink in color. That depends upon the type of particle that's dissolved. So that would not be a colligative property. However, would the intensity of that color be a colligative property? Would the intensity depend upon the amount of copper sulfate that's dissolved in my solution? Perhaps that would be. Color intensity might be a colligative property because it depends upon the amount of solute that's dissolved in my solvent. Now, the colligative properties we're really going to hit hard in this chapter are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. First up is vapor pressure lowering. Let's take a look at this illustration here. The first one shows a pure solvent in a beaker. Let's close that beaker off so the particles can't escape. Won't there be evaporation from the surface of the liquid? Remember, evaporation occurs at the surface of the liquid if the particles at the surface have enough energy to escape the attractive forces of the neighboring particles. So, if this is pure water, we have a bunch of water molecules on the surface, some at any given temperature will have the energy to escape the attractive forces of their neighbor and be able to become a vapor. They will start bouncing around in that container, slamming into the walls of the container, exerting a force. That would be the vapor pressure. Now that's pure water, and at a particular temperature, it has a particular vapor pressure. Now, let's dissolve something in that water. Let's dissolve, I don't know, some sugar in that water. It's something called a non-ionic solute. So let's say that 10% of this solution now, by the number of particles, would be sugar, and the other 90% is solvent, my water. Are there as many water molecules on the surface now? No, they're not, because some of those particles are now sugar particles, 10%. So not as many water molecules can escape the surface. Guess what that's going to do to the vapor pressure? Well, since there are fewer particles bouncing around and slamming into the walls of the container, it will lower the vapor pressure by guess how much? Well, if it's 10%, if 10% of the particles are sugar, it will lower the vapor pressure by 10%, or the new vapor pressure will be 90% of the original vapor pressure. Now that brings us to Raoult's law, which states the vapor pressure of a solution is directly proportional to the mole fraction of the solvent. Once again, if it's 90% solvent, that means the vapor pressure will be 90% of the pure solvent's vapor pressure. Now this is for something called an ideal solution, one in which all the intermolecular attractions are the same. For convenience sake, we will ignore non-ideal solutions and assume everything we deal with is ideal in this chapter. Now, mathematically, Raoult's law is P2 equals P1 times MF1. P1 is the vapor pressure of the pure solvent. Now remember, we can look that up at a table. Vapor pressure is dependent upon temperature only. P2 is the vapor pressure of the solution. And MF1 is the mole fraction of the solvent. Now remember, we found out how to find mole fraction not too long ago. Remember, that would be moles of solvent divided by total moles of my solution. and that would be MF1 in this particular calculation. Alrighty, well, let's take a look at one. Let's say that we have 20 grams of glucose. It's dissolved in 35.0 grams of water at 25 Celsius. What is the resulting vapor pressure of the solution? Now, the vapor pressure of pure water at 25 degrees Celsius is 24.0 millimeters of mercury. What will happen to the vapor pressure of that pure water when I dissolve some sugar in it? Well, if you've been listening, the vapor pressure should lower. So my final answer should be smaller than 24.0 millimeters of mercury. So, let's use Raoult's law. Raoult's law would be P2 equals P1 times MF1. So let's find the mole fraction of my solvent. Now my solvent's water. I have 35 grams of water. And we're going to go from grams to moles of water. 1 mole of water has a molecular weight of 18.02 grams. This will give me moles of water, or my solvent in this case. My solute is glucose, and I have 20.0 grams of C6H12O6. And we'll go from grams to moles of glucose. 1 mole of glucose has a molecular weight of 180.18 grams per mole. And this will give us moles of glucose. So, let's pull out our cheap calculator, and we'll find out what these values are. 35 divided by 18.02 to 3 significant figures gives me 1.94 moles of water. And then we have 20.0 divided by 180.18 gives me 0.111 moles of glucose. Now we need to find the mole fraction of our solvent. So we're going to take 1.94 moles of water divided by 1.94 moles of water plus my 0.111 moles of glucose. So 1.94 plus 0.111 equals 2.05. So we have to round this off to the nearest 100 because that's what my least accurate measurement is rounded to. So the mole fraction of solvent would be 1.94 divided by 2.05. That gives me a mole fraction of 0.946. Please, that's not my answer. That is simply MF1. So we'll say MF1 equals 0.946. Now, let's find our new vapor pressure. P2 will equal P1, which was 24.0 millimeters of mercury, times MF1, which we just calculated to be 0.946. So, we'll leave that previous answer in there, 0.946, multiply that by 24.0, and round our answer off to 3 significant figures. We end up with a new vapor pressure of 22.7 millimeters of mercury. As you can see, the vapor pressure lowered from 24.0 for the pure solvent down to 22.7 for the solution. Once again, why? Well, because on the surface of my solution I did not have pure water. I had some sugar molecules literally getting in the way of the evaporative process. Okay, next up, freezing point lowering and boiling point depression. You'll notice I have a picture here of a snow plow spreading some salt on the roads. In fact, here in Salt Lake we just experienced a nice snowstorm, and there are plenty of snow plows out not only plowing the roads but putting plenty of salt on the freeways. Have you ever wondered why they do that? Well, many of you say, well, it melts the ice. Well, in reality, what's happening is we are lowering the freezing point. So, normally, water would freeze at about 0 degrees Celsius. If I mix that with some salt and I lower the freezing point, it might freeze at -5 or maybe even -10 Celsius. So, what phase would it be in at -3 or -2? Well, if it doesn't freeze until -5 or -10, at -3 it would still be a liquid. And most of us experienced drivers know that it's much easier to drive on roads that are wet as opposed to roads that are icy. So, fact. The boiling point of a solution is higher, and the freezing point of a solution is lower than that of the pure solvent. The freezing point lowering and boiling point elevation of a solution of a non-ionic solute is directly proportional to the molality of the solution. Now we'll deal with ionic solutes next year in AP. There's not much more to learn, but it's something we don't want to worry about today. So everything that we do in this chapter and this year will be considered non-ionic. Now we're going to come back to this chart in just a few minutes. I'm going to put it off to the side for a moment. So the best way to teach this is just by working a problem or two. So let's take a look at example number 15. It says, calculate the boiling point and freezing point if 300 grams of C2H6O2 is dissolved in 800 grams of water. Well, the first thing we need to do is calculate the molality. This is why. The boiling point change is equal to the molality times K sub B. You see, the boiling point elevation is proportional to the molality. Now, we don't like proportionality signs, so we use equal signs. Whenever we do that, we need to introduce a proportionality constant. And water has a proportionality constant. We'll look it up here in just a minute. The freezing point change is also proportional to the molality, but instead of K sub B, we are going to use K sub F for, you guessed it, the freezing point constant. So, in order to do these problems, we need to find the molality. Now, we did that earlier in this chapter. Hopefully, you all know how to calculate molality. Molality is moles of solute divided by kilograms of solvent. Now, usually that solvent is water, but not always. So, let's find the molality. We have 300 grams of C2H6O2. So we need to convert that to moles. I'm going to do that right up here. 300.0 grams C2H6O2. We'll go from grams to moles. 1 mole has a molecular weight I found earlier of 62.08 grams. Divided by kilograms of solvent, which is water in this case, so that's 0.8000 kilograms of water. So the molality turns out to be, let's see, 300 divided by 62.08 divided by 0.8000. So I end up with a 6.041 molal solution. Now that's actually, oh boy, I hope you could see that. That's actually the hard part of this problem, calculating the molality. Once that's done, we just need to plug it into these equations and multiply either by the boiling point or freezing point constants. So let's see how much the boiling point changes by. The molality is 6.041 molal times the boiling point constant for water. Now let's look that up. The boiling point constant, Kb, for water is 0.51 degrees Celsius per molal solution. So, 0.51 degrees Celsius per molal solution. So let's see what that change is. We have our 6.041 in here still, times 0.51 gives us, looks like we're allowed two significant figures, a boiling point change of 3.1 degrees Celsius. Now that is not the new boiling point of my water, that's how much the boiling point changes by. The normal boiling point of water is 100.0. So if we add that to 100.0, which is the normal boiling point, the boiling point of my solution becomes 103 degrees, 0.1 degrees Celsius. Notice the boiling point has been elevated. It's about 3 degrees higher than the pure solvent. Now let's do the same thing to find my freezing point. I take the molality again, 6.041 molal, and we'll multiply it by the freezing point constant for water. So here's water, and its freezing point constant is 1.86 degrees Celsius per molal solution. 1.86 degrees Celsius per molal solution. So we'll take my 6.041 times 1.86. We'll round this off to three significant figures. I end up with 11.2 degrees Celsius. Now that is not my answer. That's how much the freezing point changes by. So normally water freezes at 0. So if the freezing point is depressed by 11.2 degrees, we end up with a negative 11.2 degrees Celsius for the freezing point of my solution. I have lowered the freezing point. Now, not only is spreading salt on roads a good example of the application of freezing point depression, but also think about making homemade ice cream and why perhaps salt is added to the ice on the outside of the container where the cream is frozen. Think about how that might lower the freezing point. It's a good thing to think about. Okay, let's do one more problem. We're going a bit long here. Don't want to go too long. We'll do this one more and we'll call it a session, okay? Now for this last one, I want to find molecular weight. So I'm giving you 23 grams of an unknown compound. It's dissolved in 1,000 grams of water. The freezing point is observed to be 0.93 degrees Celsius. Sorry, negative 0.93 degrees Celsius. What is the molecular weight of the compound? Now remember, to find molecular weight we need to know two things. We need to know grams of the solute, and that's always given in the question, and we need to know moles of the solute, and this is what we have to solve for. So let's read the question and see if we can find grams of solute. Oh, here we go, 23.0 grams of an unknown compound. 23.0 grams. Now all we have to do is calculate the number of moles. And then as you know, molecular weight is grams divided by moles. We already know the grams. Whoops. So we're going to find moles. So let's use this equation. The freezing point change is equal to the Kf times the molality. Or we could rewrite that and solve it for molality. Wouldn't molality be equal to the delta T over the Kf? Just solving for molality, I swing the K sub F over to the other side. So we have delta T over the Kf. So let's solve for the molality quickly. My delta T, let's see, the new freezing point is negative 0.93. Water normally freezes at 0. So it looks like my delta T is 0.93 degrees Celsius. We'll make that an absolute value, okay? It's just the change in the freezing point. Divided by the K sub F. So the K sub F for water, we can look that up again, is 1.86 degrees Celsius per molal solution. So we'll divide that by 1.86 degrees Celsius per molal solution. You can see degrees Celsius is divided out, and we end up with molality. So let's see what that turns out to be. 0.93 divided by 1.86 equals, well, it looks like it's 0.50 molal. I've run out of room here, so let's go to the top of the next page. We're not done yet. Keep in mind, the molality of a solution is not the same as the number of moles. My molality, 0.50, is the moles of solute, and we don't know what that is yet, divided by kilograms of solvent, which in this case is water. So that's where this comes from. We do not want kilograms of water, we just want moles of solute. So let's multiply this by the mass of water, my solvent, to get rid of kilograms of water, and then we will just have moles of solute. So, how much water did I have? Well, 1,000 grams. That's a very pretty number. Isn't that 1.0000 kilograms in this case? So the math is very simple. 0.50 times 1 is 0.50 moles of solute. In this case, the molality just happened to be the same as the moles of solute because the mass of my solvent was 1 kilogram. So now we can find the molecular weight, which is grams divided by moles. My grams, remember, was 23.0, and my moles I just solved for, 0.50. So, do we need a calculator for this? I don't think so. 23 divided by 0.5, rounded off to 2 sig figs, is 46 grams per mole. So my solute has a molecular weight of 46 grams per mole. Sort of interesting when you think about this, that you can find the molecular weight of a solute simply by finding out how much it depresses the freezing point of water. I think it's interesting. Okay, we'll do another example, maybe in a different session. Certainly we'll do it in class. Alrighty, thanks for your time.